what did the technician do when they're building up? They put it into one of these furnaces. Up it goes into the furnace. They hold it for 2 or 3 minutes at high temperature. Down it comes. They take it out, and then they repeat the process. So the object is very rapidly cooled, and particularly if it's a poor thermal conductor, the temperature before they take it out will be higher than if it's a very good thermal conductor. And what is the consequence of that? If we do that for glass, and we do it regularly for safety glass, for glass car windscreens, for glass for windows where we have safety, for instance in banks, in your bathrooms and things, we get this what are called tempering stresses. We heat this glass up to above the softening temperature, and then we cool it very quickly by blowing air on the outside, and then this causes a temperature gradient between the inside and outside, and this generates compressive stresses on the outside. Here we have these compressive stresses here, but we have tensile stresses internally. And we all know the consequence of that. If a stone hits the glass window of our car, it shatters or breaks. Why? Because the crack gets into these internal tension stresses here, and this can cause the crack to rapidly run through this system. So is this the case for zirconia? We can, there's a paper that we published a little bit a year or so ago. But first of all, what really is happening? If we have a body, for instance, a case of material, this may be porcelain, bonded to a framework, then if we now take that out of high temperature, what determines the rate at which heat will come out of that? And that's determined by this heat flux that comes out. And the heat flux is of course related to the heat transfer processes at the edge, but it is also related to how easily heat can diffuse through that system. And that is given by these typical values here, the density, the heat capacity, and the thermal conductivity, or the thermal diffusivity. And if we look at the different values for different systems, here is the porcelain, here is zirconia, and here are the other frameworks that you guys typically use for orthodontic application. Gold alloy, 3000. So it's a fantastic thermal conductor. Your stainless steel is, even though it's much poorer than gold, it's still good. Alumina, very good. But the porcelain and zirconia are extremely poor thermal conductors. I keep telling people that every jet engine in an aircraft has zirconia thermal barrier coatings on them to keep the blades or the metal cool in the process, because then they can have the temperature of the engine higher, so the thermodynamic efficiency of that engine is improved. But only because the zirconia coatings keep the metal underneath it cool. Now that's the same material we're dealing with its poor thermal conductivity in the material that we're talking about. So then we can do some simple calculations. And so here is the temperature profiles. This is 4 millimeters thick, for instance. We have a 1 millimeter coping thickness, 3 millimeter porcelain thickness. I know it's on the extreme. We cool it very quickly at 50 degrees centigrade per second. So it's very quickly cooled out of the system. Here is the alumina. Virtually no temperature gradient across the alumina. And then there's a small temperature profile through the porcelain. In the case of zirconia, you see this tremendous thermal gradient through the zirconia and much higher temperatures that are occurring in the porcelain. Now the problem is that now, as that cools through this glass transition from the softening temperature to the glass transition temperature, that locks in this temperature gradient. Why? Because during when we're above the glass transition temperature, there is relaxation of stresses. But as soon as we get to the glass transition temperature, it acts as a rigid body, and now it freezes in this temperature difference. So the outside cools first, but the inside continues to cool down, and so it is contracting and thereby sets up tension internally with compensating compression at the surface. And we can look at this. So here is an example of where we have this thermal expansion mismatch stresses, because there's a difference in the coefficient of thermal expansion, and that's that pink line that crosses there. Here are the tempering stresses. We can add the two, and this gives the yellow line that goes through. And that's in your porcelain material. So in the middle of your porcelain, we have these large regions of high tension that can develop. It's more complex in I've just taken a plate example here, and we can do other examples as well. And here is the case for the alumina, and you can see that even in alumina we get a small amount of compressive tensile stress, but look in the zirconia, it's 3 to 5 times higher in terms of that tensile stresses that developed internally in that system. Now, is this really true? Theory is one thing, does it match with the experimental? So this is some work done by a student, and he's on final year student as a dental technician at Dunedin at Otago University. So he made these 2 different systems. Here is the zirconia coping, sort of layer. Here is the porcelain, 4 millimeters, and here is 2 millimeters thick. He then cooled one very slowly by leaving it in the furnace and just bringing it down very slowly. And in the second one, he cooled rather quickly by holding a jet of air, just like if you had the window open on a hot day and the cool air is blowing through. So this is cooling down, simulation, that circumstance. And what do we see? The temperature difference. So here is where we have the temperature difference on the inside. So at high temperature, there is no difference in the furnace. Now when we take the furnace or pull it out of the furnace, you see this difference. The outside or the surface temperature is much lower than the inside. And that's because of the poor thermal conductivity of that system. I know of other people that have measured temperature differences exceeding 150 degrees centigrade because of this rapid cooling. What are the consequences? When we do, one way to simply see this is we can do an indentation, and then with a Vickers indenter, and we can measure the size of the cracks that develop around that. We can do this on a very slowly cooled sample that's polished, so there's no residual stresses. We can measure the size of the cracks, and we can do it on systems, for instance, that are bonded. And here we have a residual stress of about 5 megapascals under slow cooling. But if we fast cool that material, same magnification, but now notice how small these cracks are. And so that has got a compressive stress in the surface of 60 megapascal compression. There is 30 megapascal tension, internal stress in that system. What's the consequence of that? Well, this student went away after he did this and had a cup of coffee, and when he came back, this is what he saw. This one there was no change, the slow cool system. But the fast cool system, you may be able to see, but a crack ran completely through that system. Why? The residual subsurface tension stresses, the crack was able to grow into this area and then rapidly run completely through that system. Now, is this occurring in other systems? Yes, here is another example from Suzanne Shearer at Geneva, and this is the case of a complete cusp that completely broke off that material. Again, on zirconia, you see this complete crack growth that is occurring in that system. It's not initiating somewhere, and again, she's done a complete fractographic analysis of that system, showing that the crack is starting in here, then growing within the system, and there's tensile residual stress, and then chipping out afterwards.